Let's apply our statement of the second law to a gas that is expanding and see if we can figure out how much the entropy changes when that system expands. First, let's look qualitatively at two possible ways that we can do this expansion. We can expand the gas isothermally, in which case heat must enter the system as work leaves the system so that the final temperature and the initial temperature remain the same, and thus we have an isothermal process. We could do the process adiabatically, in which case no heat enters or leaves the system, and in that case, when we expand, the final temperature will end up being less than the initial temperature. We can think of our gas particles as being particles in a box contained in the piston. Remember that the correspondence principle introduced in Chapter 2 tells us that as we increase the domain or the size of the box, that the energy levels become more and more closely spaced and we go more and more towards the classical limit. If the energy levels are more and more closely spaced, then there are more microstates available to the system with the larger volume than there are to the system with the smaller volume. That larger number of microstates means that we are going to have an increase in the entropy of the system when the volume increases because we increase the number of microstates available to the system. The same thing is true in the adiabatic case. However, in the adiabatic case, our final temperature is lower than our initial temperature. When I have a lower temperature, I have less microstates that I can access because I have less total energy, kinetic energy in the system. And so the decrease in temperature compensates for the increase in volume, leading to a total entropy change of 0, in this case, because I've done the process reversibly and adiabatically, and the second law tells me that delta has to equal 0. Again, this is because the entropy increases with the increase in volume, but the entropy decreases because there are less microstates available as the temperature decreases. The increase in entropy and the decrease in entropy compensate to give a total entropy change of 0 in the adiabatic case. To calculate the change of entropy in the isothermal case, we recognize that we want to calculate a change in entropy when the volume is changing at constant temperature. Recall that solving problems in thermodynamics always begins with a partial derivative. Our next step is to find an expression for this partial derivative. Recall, using Maxwell's relations, that this partial derivative is also equal to how the pressure changes with temperature at constant volume. If I have an ideal gas in my piston, then the pressure is equal to nRT over V. And so the derivative of the pressure with respect to temperature at constant volume is nR over V. Making that substitution, we can write that the derivative of the entropy with respect to volume at constant temperature, which is what we're after, is equal to nR over V. From here, the next step is to separate variables and integrate. So ds is equal to nR over V dV. And now I'm going to integrate from my initial state to my final state. And in my initial state, I have an initial volume. In my final state, I have some final volume. And when I do these integrals, the first one gives me delta S, the one on the left-hand side. The right-hand side gives me nR, because those are constant, natural log of V final over the initial. It's very important to always remember what assumptions you made in deriving any equation. Notice that we made the assumption that the gas in our cylinder was an ideal gas. Therefore, this equation will only work if my system is composed of an ideal gas. It does not work if my system is a real gas or a liquid or a solid. To calculate the change in entropy for one of these systems, I simply need to use the appropriate equation of state and take the appropriate derivative, separate the variables, and integrate. Notice that in the isothermal expansion, some heat from the surroundings or from the reservoir must enter the system. So it's instructive to look at what happens to the entropy of the reservoir, because the reservoir must have lost heat if the system gained energy as heat. During a reversible expansion, we know that the system gains energy as heat. However, the system also loses energy as work, and so the total change in internal energy of the system is Q plus W. So we can represent that graphically in this way. The amount of heat input to the system is equal and opposite to the amount of heat that the surroundings have lost. If I do the process reversibly, this is equal to the amount of heat transfer that I'm going to use to calculate delta S for the system. And since the heat lost by the surroundings is equal to the heat gained by the system, we can see that delta S of the system is equal and opposite to the delta S of the surroundings. But what happens if I do this process irreversibly? Because energy is a state function, I know that the total change in energy must remain the same. However, we know that when we do work on the surroundings, the maximum amount of work we can do is when we do it reversibly. And so the amount of energy that I transfer to the surroundings as work in the irreversible case has to be less than in the reversible case. Thus, we can see that the amount of energy input as heat in the irreversible case is less than the amount of heat input in the reversible case. The energy that gets transferred to the system from the surroundings is equal to the Q irreversible. So the irreversible amount of heat is equal to the heat lost by the surroundings. That heat transferred from the surroundings is transferred reversibly, and so when I calculate delta S for the surroundings, I have to use the irreversible, the actual amount of heat that gets transferred. However, to calculate delta S for the system, I must use the reversible amount of heat, because the second law tells me that I must imagine a reversible process. Thus, in this case, it's easy to see that the entropy lost by the surroundings is less than the amount of entropy gained by the system, because Q irreversible is less than Q reversible. So whereas in the reversible case, the amount of entropy lost by the system equals the amount of entropy gained by the surroundings, in the reversible case, we can see that the system has gained more entropy than the surroundings have lost, and therefore the total change in entropy is positive as required by the second law.